go to the custom queue underscore custom queue event method and write code to call the process items method. Let's run the code. Now you can see that when the queue is populated with 5 items, the items are processed and each item is removed from the queue once the relevant item has been processed. When the queue is empty, the next 5 items are added to the queue, and once 5 items have entered the queue, the items are processed one by one until the queue is empty. Great! So to further clarify to the user the status of each item in the queue, let's write the message property of the event args object to the console screen. This message property contains a narrative describing the relevant item and the event pertaining to the item. Let's run the code. Excellent! The supervisor can see relevant information about the item as well as the event. The supervisor can see status output for each item as it enters the warehouse and is processed. The final thing to do is enhance the formatting of the output. In the interests of time, let's copy and paste relevant formatting functionality from GitHub. So let's navigate to this location in our browsers. And please feel free to copy my actions here. Let's copy the code situated between the 2 comments that have the text headings. Let's then paste the code into our code editors. We can then write the code to call these output formatting related methods at appropriate points within the custom queue underscore custom queue event method. Great, let's run the code. Excellent. So lastly, I'm going to put a few breakpoints in the code to clarify the execution path of the code. So in the calling client code, when the code adds an item to the custom queue, you can see the event that resides in the custom queue class in the Warehouse Management System API component is raised, and the code in the calling client handles the event through a method that was designated to handle the event when the calling client code subscribed to the relevant event. When the predefined batch size of 5 has been reached, i.e., when the custom queue contains 5 items, each item is processed. Once an item has been processed, it is removed from the queue. The event is raised to the client, and the client method that has been designated to handle the event is executed. When the calling client subscribed to the event in the custom queue class, a method that resides in the calling client code was designated to handle the event. When the event is raised, the relevant event handler method is executed. In this event handler method, we are writing status information to the screen so that this information is available to, for example, a supervisor in real time. I hope you have enjoyed this video, which demonstrates the use of the C# generic built-in queue data type, a generic class with constraints, and the use of a generic delegate used to define an event. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. If you feel you have gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. Your comments are of course always welcome. The code created in this tutorial can be downloaded from GitHub. Please see a link to the relevant repository below in the description. Hi and welcome. This video is the fourth and final part in a video series on C# generics. The C# generics video series is the fifth part of a course on advanced C# concepts. In this video, we are going to first look at how, in terms of generics, the MSIL code, or Microsoft Intermediate Language Code, is handled by the Common Language Runtime under the hood, as it were. If you stick around till the end, I'll show you how a utility that ships with Visual Studio for Windows, named Intermediate Language Disassembler, can be used to disassemble an assembly, whereby the MSIL code can be extracted from the .NET assembly and inspected. We'll then look at a basic code example whereby the factory design pattern is implemented and generics supplied to our factory class so that this class can be reused to instantiate multiple types. We'll apply multiple constraints to our factory class to enforce design rules driven by the requirement for our code example. For more videos on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future releases from this channel. So let's briefly look at how generics in the MSIL code, or Microsoft Intermediate Language Code, is handled by the Common Language Runtime. I'm not going to go into a lot of detail in this regard, but please check out this Microsoft document for a more detailed description regarding how generics is handled by the .NET Runtime. This document explains how generics is handled differently for value types and reference types by the .NET Runtime. Let's look at a few excerpts from this document. Specialized generic types are created one time for each unique value type that is used as a parameter. This means conversions are no longer necessary because each specialized generic class natively contains the value type. Generics work somewhat differently for reference types. The first time a generic type is constructed with any reference type, the runtime creates a specialized generic type with object references substituted for the parameters in the MSIL. Then, every time that a constructed type is instantiated with a reference type as its parameter, regardless of what type it is, the runtime reuses the previously created specialized version of the generic type. This is possible because all references are the same size. Because the number of reference types can vary wildly from program to program, the C# implementation of generics greatly reduces the amount of code by reducing to 1 the number of specialized classes created by the compiler for generic classes of reference types. So, two benefits are highlighted in this document with regards to value types and reference types in terms of generics. Conversions are no longer necessary because each specialized generic class natively contains the value type. Generics greatly reduces the amount of code by reducing to 1 the number of specialized classes created by the compiler for generic classes of reference types. My goal here was only to draw your attention to the extra information regarding how the .NET Runtime implements generics in C# under the hood, as it were. Please read this document to gain a better understanding in this regard. So let's implement our code example where we'll implement the factory design pattern and use generics so that the object instantiation code is abstracted and can be used to instantiate multiple types. We'll use multiple constraints appropriate to our requirement so that special rules at compile time are enforced. Let's create a .NET Core console app and let's name it Digital Product Inventory Application. So in this very basic example, we're going to create classes for representing specific types of digital products. We'll also create classes for encapsulating data associated with the various categories of digital products. We are going to create a factory class used to abstract and centralize the construction of these different types into objects. We'll then copy code from a GitHub repository, and this code will serve as the calling client code. This client code includes a LINQ query used to compile a report containing digital product information and their associated digital product category information. Code is also included to output the results of this LINQ query to the console screen. This example is more about understanding the application of generics than understanding LINQ. Please don't worry if you don't fully understand the LINQ aspect of this tutorial. LINQ will be discussed in detail in upcoming tutorials. So let's create our factory class. This tutorial is not about design patterns, but the factory design pattern is used in this example as a device to show how generics and constraints can be implemented to abstract the construction of objects of varying types. Special rules will also be applied through the use of constraints. Let's name this class Factory Pattern. So this class contains two generic types. So let's include the constraints for the type T parameter in our definition of the Factory Pattern class. As we know from our previous tutorials, constraints enforce compile time rules on our type parameters. So this constraint is enforcing a compile time rule that type T must be a reference type denoted by the class constraint, must inherit from type U, i.e. the other generic type parameter, and the type T argument must also contain a public parameterless constructor. This is denoted by the new constraint. Note that when the new constraint is used with other constraints, the new constraint must be specified last. In our code, we are going to instantiate an object of type T. Note that a generic type cannot be instantiated if the new constraint is not specified for the type that must be instantiated. We'll prove this in a bit. So let's also add a constraint to our uType parameter. We can do this by including another where keyword, followed by the relevant constraint or constraints for the U data type. Note that this class constraint for this example is in fact redundant for the U parameter, and I will remove this from the relevant GitHub repository. I'm applying this constraint at this point in the tutorial to show how we are able to apply constraints to multiple type parameters. So let's add a method to our class and name it getInstance. So the code logic for this method is instantiating an object of type T, which is derived from type U. The instantiated object is then returned to the calling code. So now, just to show you that we cannot instantiate an object of type T unless the new constraint has been appropriately applied to the relevant class definition, let's comment out the new constraint. And you can see that the C# compiler immediately complains. We must ensure that we have appropriately applied the new constraint in order to be able to create an instance of type T. So let's now create an interface named iPrimaryProperties. Let's add two property definitions to our interface, ID as int and title as string. So now let's go back to the factory pattern class. Let's add a constraint to enforce a rule that type U must implement the iPrimaryProperties interface. So we can do this by adding a constraint like this. Remember, the class constraint can be removed from the uType parameter. The code will still work as expected with it there, but for this example it is redundant. So let's add an abstract class named ProductBase that implements the iPrimaryProperties interface. Let's implement the properties defined in the iPrimaryProperties interface as auto-implemented properties. Let's create an abstract class named CategoryBase that also implements the iPrimary Properties interface. Let's extend the product base class by adding an auto-implemented property named Category ID. The Category ID property will be included within our link query to join the data stored in a list containing objects of type category base to relevant product objects stored in a list containing objects of type product base. We'll look at the link query in a bit. Let's extend the category base abstract class and add an auto-implemented property named description. So let's create our category classes. Let's create our digital product classes. So our category classes inherit from the category base abstract class, and our product classes inherit from the product base abstract class. Note that both the product base abstract class and the category base abstract class both implement the iPrimary Properties interface. Notice I am extending these classes with additional properties just for demonstration purposes. These additional properties won't be used further than this in this example. So I'm going to create a class named Product View Model, and this class will be used as a template to centralize information from the product-related classes with information from their relevant category-related classes. So we want our calling code, which we'll copy from GitHub, to create several product objects and related category objects. Then using link, we'll return a collection of objects of type product view model to the calling code. This collection will be the result of a join operation, joining objects of type product base with the relevant objects of type category base. Link is not the focus of this tutorial, but I thought I'd include the link functionality to make our example more interesting. As stated earlier, we'll discuss link in detail in upcoming tutorials, so don't worry if you don't understand the link-related code. So I've already uploaded the code for this example to GitHub. So let's copy the code, which will serve as our calling client code, from the relevant GitHub repository, which can be found at this location. This URL has also been included below in the description. Let's copy all the code from within the program class like this. And let's select the main method within our program class in our code editors and paste the code we have copied from GitHub over the main method in our code editors like this. And you can see that we have red squiggly lines under our code relating to our generic lists. So to fix this, let's add a directive to the system.collections.generic namespace. And in our getProducts method, where we are executing a link query, we have a red squiggly line here. So to fix this, we need to add a directive to the system.link namespace. Great. So let's look at the calling client code we have just copied from GitHub. The add properties to product method encapsulates functionality to add values to the properties of an object of type product base. The add properties to category method encapsulates functionality to add values to the properties of an object of type category base. You can see that these methods are currently public methods, but they don't need to be public, so we can change these methods to private. I'll update the relevant GitHub repository with this change. You can see here that our link query is encapsulated in a method named getProducts. The link query is selecting all product-related objects in the products list and joining each product with its relevant category. Each product is joined to its relevant category through the category ID property. The result of the link query is a collection of objects of type product view model, which appropriately combines product information with relevant category information. As stated earlier, LINQ will be discussed in detail in upcoming tutorials. So let's look at the code in the main method. So notice how the factory pattern generic class is being used to instantiate each object of type product base. For example, we are instantiating an object here which represents a digital book entitled The Old Man and the Sea. We are instantiating an object here representing a movie entitled Shawshank Redemption. The factory pattern generic class is then reused to instantiate several objects of type category base. For example, we are instantiating an object representing the category with the title of movie here, and we are instantiating an object representing the product category here with the title of music. So the factory pattern class has been implemented to abstract the object creation functionality for this code example. We have adapted the factory design pattern to our requirements by imposing rules on the instantiation process through the use of constraints. So in the main method, we are instantiating our product-related objects, appropriately adding values to the relevant object's properties, then adding the objects to a list of product-related objects. We are doing the same thing for our category-related objects. We are then appropriately amalgamating information from the product-related objects with relevant information from the category-related objects into an object of type product view model through the use of a LINQ query. We are then looping through the items returned from the LINQ query and writing each item's properties to the console screen. So let's run the code. Great. I want to draw your attention back to the constraints in our factory pattern class. Note that we have implemented a constraint that the U argument must implement the I primary properties interface. So if, for example, we were to comment out the code in our class definition for the category-based abstract class that indicates that this class implements the I primary properties interface, look at how the C# compiler responds. Note how the constraint imposes a rule at compile time that the U argument must implement the I primary properties interface. For more detailed information on constraints, please navigate to this URL. So we were discussing earlier how the .NET Runtime handles generics based on the MSIL code. We are able to examine the MSIL code for an assembly by using a utility like, for example, the IL disassembler utility. So now, if we wanted to look at the MSIL code for this project, we can use this utility. This utility ships with the Visual Studio for Windows IDE. So let's run our developer command prompt for Visual Studio. Let's make the directory where our target assembly file resides our current directory. We can then type the following command. This command generates a file containing the MSIL code within the directory of the relevant assembly. This is the MSIL code that resides within the target assembly, created when we built our C# project. So now we can open the file we have just created in a text editor like Notepad and look at the relevant MSIL code. Great! For more detail on the IL disassembler, please navigate to this URL. All URLs mentioned in this tutorial can be found below in the description. Lastly, if you are interested in reading about generics and reflection, please navigate to this URL. If you are interested in reading about generics and attributes, please navigate to this URL. Reflection can be used to inspect generic types in C# at runtime, and this will be discussed in later videos created on C# Reflection. Generics used with attributes will be covered in future videos created on C# attributes. In this video series, we discussed that generics was introduced in C# version 2. We looked at why it is better to use a strongly typed generic list to store a collection of items rather than an array list for this purpose. We discussed the benefits of generics. Generic classes and methods combine reusability, type safety, and efficiency in a way that their non-generic counterparts cannot. We looked at how constraints can be applied to generic type parameters in order to enforce compile time rules on generic type parameters. We created a code example representing a warehouse management system. In this example, we used the built-in C# generic queue collection type to store objects representing various hardware items that enter the warehouse and are subsequently processed. Generic delegates and events were instrumental in this real-time monitoring system. Lastly, in this video, we briefly looked at how the MSIL code, or Microsoft Intermediate Language Code, is used by the .NET runtime to efficiently handle both value types and reference types in terms of generics. We also implemented a generic version of the factory design pattern in a basic code example to demonstrate how the use of multiple constraints can be applied to generic types in order to enforce special, requirement-driven compile time rules. I hope you have enjoyed this video series on C# generics. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. If you feel you have gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. Your comments are of course welcome. The code created in this tutorial can be downloaded from GitHub. Please see a link to the relevant repository below in the description. Hi and welcome. This is the 6th tutorial in an advanced C# course, and this is the first part of a video series on asynchronous programming using the C# programming language. In this video, we'll look at an overview of asynchronous programming in C# with a particular emphasis on Microsoft's recommended approach to using asynchronous programming for new development. Microsoft's recommended approach to including asynchronous behavior in new applications is to use the task-based asynchronous pattern, TAP. The two legacy methods for providing asynchronous behavior are event-based asynchronous pattern, EAP, and asynchronous programming model, APM. The event-based asynchronous pattern will not be discussed in this video series, but if you wish to learn more about this legacy pattern, please navigate to this URL. We have already covered the asynchronous programming model, APM, in the advanced course. In part 3.5 of this course, we looked at using a callback method and a built-in delegate to implement asynchronous behavior. Please navigate to this URL to view a video released on this channel that covers the asynchronous programming model, APM. As always, all links mentioned in this video can be found below in the description. Later on in this tutorial, we'll look closer at how using the task-based asynchronous pattern can result in asynchronous behavior for our applications and ultimately ensure that our users have a smooth user experience when using our applications. For more videos on advanced C# topics and much more, please consider subscribing, and please ring the bell so that you'll be notified of future videos released from this channel. Right, so TAP, or Task-Based Asynchronous Pattern, is the recommended design pattern for creating asynchronous behavior for new development. C# version 5 produced a simplified approach to asynchronous programming that leverages asynchronous support in the .NET Framework 4.5 and higher, .NET Core, and the Windows runtime. .NET Framework 4.5 or higher and .NET Core contain many members that work with async and await. These members can be identified by their names, which contain an async suffix. So what gave rise to the task-based asynchronous pattern? We live in an age where our applications should not only run on desktop computers and notebook computers, our applications in a lot of cases will also need to run on smaller devices. For example, handheld devices like tablets and mobile phones. These smaller devices may not have the powerful resources that desktop computers and notebook computers have to handle resource-intensive operations. So, an operation like, for example, downloading a large document from a remote server may ultimately result in poor performance of our applications. A poor UX, or user experience, with our applications can cause user frustration and cause our users to take a dim view of our applications. Implementing this pattern in our code can result in a smoother UX, user experience. The code is easy to implement, and even though the code results in asynchronous behavior, the code can be written in a synchronous way. We'll look at a code example to further elucidate this point in a bit. The C# compiler makes it very difficult for a developer to implement the task-based asynchronous pattern incorrectly. For example, in an IDE like Visual Studio, red squiggly lines will appear in appropriate regions of code if the relevant asynchronous code has been written incorrectly. Messages will also be made available to the developer from the C# compiler in Visual Studio to guide the developer on how to fix the incorrect code. So, how can long-running operations result in a poor user experience with our applications? Say, for example, a button is clicked, and within the event handler method of the relevant button click event, a long-running operation is invoked. If this operation were to be invoked synchronously, the thread of execution on which the relevant time-consuming operation is running is blocked until this long-running operation has completed. While the relevant thread is blocked, the application is unresponsive, meaning the user cannot perform other operations with the application until the long-running operation completes. So this ultimately results in poor user experience with our application. There are two kinds of blocking operations: CPU-bound operations and I/O-bound operations. So let's look at CPU-bound operations. This occurs when an intensive computation needs to be carried out by the device's CPU. For example, you might have a game running, and a single action from the user may cause multiple characters in the game to incur damages. The calculations of these damages may be CPU intensive. An operation like this, if done synchronously, can result in the UI to freeze or stutter. Running the calculations in parallel across multiple cores can alleviate this and make the UI, or user interface, perform smoothly and responsively. So the developer could use the task.run method to run calculations in parallel to alleviate the effects that handling these computations synchronously could have on the user's experience. Other examples of applications that may need to run intensive CPU-bound operations could be financial or scientific applications. So let's look at I/O-bound operations. I/O-bound operations are performed when requesting data from a network, accessing a database, or reading and writing to a file system. The blocking effect during an I/O-bound operation causes the CPU to wait for the relevant I/O-bound operation to complete. So the CPU will need to wait, basically lie dormant, while, for example, information is retrieved from an Azure SQL database that resides in the cloud. Once the information is retrieved and, for example, appears in local memory, the information can then be processed by the CPU. The CPU can only then continue processing other instructions. While the I/O-bound operation is running, the CPU is blocked from running any other operations. Performance will not be optimal for our applications when the code for these relatively long-running operations are handled synchronously. I/O-bound operations are the most common encountered blocking operations. So we are going to focus on resolving the blocking effect of I/O-bound operations through the implementation of the task-based asynchronous pattern in this video. Note that generally speaking, I/O-bound operations are far slower than CPU-bound operations. In business applications, I/O-bound operations will be far more common operations that will be encountered and should be handled asynchronously. And let me emphasize, I/O-bound processing is far slower than CPU processing. So let's look at a basic code example. We won't implement this particular code in Visual Studio. This code serves to give us a general idea of what the task-based asynchronous pattern looks like in C# code, and we'll also get an idea of how it works. Let's first look at the synchronous version of this code example. We'll then modify the code so that it is implemented using the task-based asynchronous pattern. So in this synchronous version of the code example, we have a high-level button-click event handler named button_click. When the user clicks the button that invokes code within this event handler method, a call to a method named getDocumentContent is made. This method accepts an argument, which is the name of the remote file that our code needs to retrieve and process. So let's say that the path of the remote document is handled under the hood, as it were. A relatively long-running operation is encapsulated within a method named getDocumentContent_string, which is invoked within the getDocumentContent method. The long-running operation in this case is downloading a document from a remote server. After the long-running operation completes, a string is returned from the getDocumentContent_string method containing the relevant document content. A method named saveDocumentLocally is then called, which, as the name suggests, saves the content returned from the getDocumentContent_string method to a local file store as a new file. The document content is then returned to the calling code from the getDocumentContent method. Once the getDocumentContent method completes and returns the content to the button-click event handler method, the content is subsequently displayed to the user. This is denoted by a call to a method named displayContent. So while the code is performing the relatively long-running operation executed by the getDocumentContent_string method, the thread of execution on which this operation is running will be blocked, leaving the CPU idle until the getDocumentContent_string method completes and returns a value. So let's say that we are in luck and there is an asynchronous version of the getDocumentContent_string method available to us named getDocumentContent_string async. Note that this version of the method has the same name as the synchronous version, with the exception of the async suffix added to the end of the method's name. Adding the async suffix to the end of an asynchronous method's name is a naming convention used for asynchronous methods that are part of the implementation of the task-based asynchronous pattern. So the method we want to call is named getDocumentContent_string async. So we need to use the await operator preceding the method call to the getDocumentContent_string async method like this. This is telling the C# compiler that we wish to call this method asynchronously. If any of our method calls within the getDocumentContent method are awaitable, as is now the case here, where we are using the await operator, we need to include the async modifier in the method signature of the method where one or more asynchronous method calls are invoked, which, as stated, is denoted by the await operator preceding the relevant asynchronous method being called. So let's include the async modifier in the method signature for the getDocumentContent method. Let's also adhere to the correct naming convention, so let's rename the getDocumentContent method to getDocumentContent_async, like this. The getDocumentContent_async method will return a string value once the async method has completed, but when it is first called and hasn't necessarily completed, a generic task object will be returned. I'll elaborate on what the task object and the generic task object is in a bit. So we must include the relevant generic task type in the method signature of the getDocumentContent_async method like this. We are calling an asynchronous method from the button-click event handler named button_click. So we need to include the await operator preceding a call to the getDocumentContent_async method like this. We are now calling an awaitable method within the button_click event handler method, so we need to include the async modifier within the method signature of the button_click event handler method like this. We don't need to include a task type in the button_click event handler method signature because it is a high-level event handler. All asynchronous methods that are not high-level event handlers like the button_click event handler will return a task object if the relevant method does not return a value, or a generic task object if the relevant method does return a value, as is the case with our getDocumentContentAsync method, which returns a string. So, for example, the getDocumentContentAsync method returns a string value once it has completed. So to reflect that this method is an async method that returns a string value, we include the generic task type in its method signature, and this generic task type accepts the string data type as its argument. So basically, the new asynchronous implementation of this example code means that when asynchronous methods are called with the await operator, the control is immediately returned to the calling code, meaning that the thread of execution on which it is executed is free to process other operations while the asynchronous method is running. So the CPU is not left idle while an I/O-bound operation is underway, as is the case in this example where a file is retrieved from a remote server. In this asynchronous implementation, the CPU thread of execution on which the relevant, relatively long-running operation was invoked can be used to perform other operations while the remote file is being retrieved from the remote server. In this case, the UI thread is the thread of execution. So if, for example, the user needed to execute a different button-click event, another operation could run concurrently to the long-running operation invoked by the getDocumentContentAsString method. This means the user's experience with the application will not be negatively impacted by this relatively long-running operation. The user experience is not adversely affected by the relatively long-running operation performed by the getDocumentContentAsString method. So when the getDocumentContentAsString method is called, a generic task object is returned immediately to the calling code. The string value that is returned only once the getDocumentContentAsString method completes is returned at that point of execution in the code, but at a later time. While the relatively long operation invoked by the getDocumentContentAsString method is running, other operations can be performed by the user without negatively impacting the user's experience with the relevant application. Basically, the task object is a state machine. If you'd like a comprehensive explanation of what a state machine is, please navigate to this URL. The task object encapsulates information about the asynchronous process and either delivers the final result back once the asynchronous method completes or throws an exception if an exception occurs within the asynchronous method. So we can put traditional try-catch code around the call to our asynchronous methods as if the methods were synchronous to handle exceptions that may occur in our asynchronous methods. So when the awaitable method is executed, a task object is immediately returned to the calling code. The string value is only returned later once the awaitable method completes. When the task object is returned, the relevant thread of execution is then immediately released to the caller. The thread of execution is not blocked while the asynchronous operation is running. So the async method first returns the task object, in this case a generic task object, that promises to return a string value at this point in the code once the operation performed within the relevant async method has completed. This model is known as the promise model of asynchrony. If you wish to read more about the promise model of asynchrony, please navigate to this URL. On the C# side of things, the C# compiler transforms your code into a state machine that keeps track of things like yielding execution when an await is reached and resuming execution when a background job has finished. The async modifier is doing two things. Number one, it is a message to the C# compiler that this method can use the await operator inside it. The await operator designates the suspension points in the execution. Number two, the method itself can be awaited by methods that are calling it. The async modifier also is a message to the C# compiler that the method can be called asynchronously using the await operator. The await operator is telling the compiler that the execution of code cannot continue past this point until the awaited method has completed. So in the meantime, control returns to the caller of the method, which is the UI thread in this case, which allows, for example, the user to click other buttons while the incomplete asynchronous task is still running. Under the hood, as it were, when you compile your code through Visual Studio, the C# compiler rewrites your code into intermediate language, splitting apart your async method calls into lots of callback methods. So we as coders don't need to worry about the complexity of implementing callback methods ourselves. With this explanation, I'm admittedly, in the interests of brevity, glossing over a mass of complexity involved in making this asynchronous abstraction model work. For more detail and a comprehensive diagram of how the underlying framework is handling the asynchronous code, please navigate to this URL. Note that the line of code that includes the await operator is in fact doing two things. It is returning a task object when it is first invoked, and then later, when the asynchronous operation completes, it is returning the value returned by the relevant method, in this case, a string value. So we can write the code like this to make this clearer. We could first assign the task object returned by the relevant asynchronous method to a variable of type task. This is done without the await operator. We can then call the relevant task object with the await operator later in the code. In this case, the string value will be returned from the task object when the relevant operation completes. In this particular example, we can write what is achieved by 2 lines of code here in 1 line of code like this. So let's put the code back to how we originally had it. So let's create a code example. We are going to create 2 .NET projects. One project will represent the calling client code, i.e. the code that will contain the user interface. The other project will represent the server-side code. The calling client will be implemented as a UWP project, or Universal Windows Platform project. The server-side code will be implemented as a Web API project. This example is very basic. We'll implement a button-click event handler on the user interface, which will be included within the UWP project. Code within the relevant button-click event handler will asynchronously call a method included within the Web API server-side component. In the relevant Web API action method, we'll deliberately implement a delay to represent a task that is relatively time-consuming and should be awaited by our client code, i.e. should be called asynchronously. We'll implement another button-click operation on the UWP project's user interface, which will implement code that runs a much faster local operation. We'll run the code and demonstrate that when clicking the button that kicks off the time-consuming operation implemented in the Web API code, that this does not impede the user's experience, and the user is able to click the second button, which carries out a much faster local operation. Perhaps the user can click this several times while the application is awaiting for the more time-consuming operation carried out on the server side to complete and return a value to the calling client code. We'll prove that the fast local operations can run concurrently while longer asynchronous operations are running in the background. And because we have written the long-running operation to run asynchronously, that the user's experience is not adversely affected by running the relatively long operation. So let's create a Web API project and let's name this project Test Time Consuming Operation Web API. Note that when the Web API project is created, a controller class is automatically included in the Web API project. This automatically included class is named Weather Forecast Controller. Code within this controller simply outputs made-up data representing a weather forecast. We'll come back to this Web API project in a bit and create our own controller class. Let's create a UWP project and let's name this project Test Client Async UWP. Okay, so let's go back to the Web API project and let's create a Web API controller class. And let's name this controller TestLongOperationController. So the code in this method is faking a relatively long running operation that needs to be performed before returning a value to the client code. The call to the server-side component's relevant action method will be handled through an HTTP GET request from our UWP project. We'll write the code for this in a bit. Please note that this tutorial is not about UWP or Web API, so I'm not going to go into detail explaining these two types of projects. The focus is on writing code using the task-based asynchronous pattern in C# to ensure that the user's experience is not adversely affected by long-running operations, perhaps being run remotely through a Web API call. So note that we are not only going to use the task-based asynchronous pattern on the client side, we are also using the task-based asynchronous pattern for this action method in the server-side code. We have discussed how client-side UI synchronous code can negatively affect the user's experience, and that implementing the task-based asynchronous pattern on the client side can make the user's experience much smoother. The task-based asynchronous pattern can also be implemented for server-side components like, for example, a Web API component or an ASP.NET MVC component. This creates better performance on the server side, which ultimately can affect client-side UI responsiveness. On the server side, it means, for example, that the thread of execution on which a relatively time-consuming method runs will not be blocked while the relevant time-consuming operation is performed, and the relevant thread can handle other requests while the relatively time-consuming operation is running. In terms of the user's experience, if a time-consuming operation blocks the thread of execution because of synchronous code, this could tie up server-side resources, causing a delay in performance on the server side, and at worst, could cause, for example, a client's HTTP request to time out. So, server-side synchronous code can also adversely affect the user's experience. So in order to fake the long-running operation, I'm simply going to create an await statement and use the task class's delay method to pause the method at this point for 5,000 milliseconds. In other words, it will cause a delay of 5 seconds. Once the 5-second delay representing our long operation is finished, the code returns a string value. So let's return the text Web API long-running operation completed to the calling client code. So let's test the code. And you can see that the output from the weather forecast controller code is written to the browser window. Let's change the URI in our browsers to point to the controller code that we have just created. So let's make a GET request to our TestLongOperationController. Great! There is a clear delay of 5 seconds before the expected string result is written to our browser windows. Okay, let's write the calling client code in our UWP project. So, we are going to drag 2 buttons onto the design surface from our list of XAML controls. Let's drag our first button onto the design surface. Let's enlarge our button a bit. Let's name this button BTN Local Operation. Let's label this button Local Operation. So let's zoom in a bit so we can have a clearer view of our button. Let's drag our second button onto the design surface. So let's enlarge this button a bit. Let's name this button BTN Web API Call. Let's label this button Web API Call. So let's drag a list view component onto our design surface. You can see the list view is currently the same size as our design surface and is covering the whole design surface. Let's resize it so its contents will appear to the right of our buttons. Let's name our list view component LVW Output. You may have noticed that creating a beautiful design for our UI here is not a concern for this video. But in the interests of saving time, this design will be adequate for what we are demonstrating here. It might be a good time to make the point that UX is not just about aesthetics, which of course is very important, but it is also about performance. We are focusing on how we can write asynchronous code to drastically improve the user's experience. So let's go to the code behind our design surface and let's write a private method named addListItem. And here we are writing a piece of reusable code for adding a string value to our list view component. Within each of our two button click event handlers, we want to add relevant string results to our list view component. We'll write the code for the two button click event handlers in a bit. Let's create two integer member variables, one named _local operation counter and the other named _web API operation counter. Let's write the code that executes when the button that performs the fast local operation is executed. So we can auto-generate the method signature for the relevant button click event handler method by double-clicking on the relevant button on our design surface like this. So when this button is clicked, we want to increment the _local operation counter integer member variable by a value of 1 and append this integer value to the literal text fast local operation completed. We are adding this string value to the list view component that we named LVW output through a call to a private method named addListItem. So let's implement the code to call the Web API method that implements the long-running operation. And we want this code to fire when we click the button we have named BTN Web API Call. So let's double-click the relevant button on our design surface to auto-generate the relevant button click event handler method like this. So the code here is a little bit more involved than the code that runs when the user clicks the button we have named BTN Local Operation. Let's first write the code to increment the _web API counter integer member variable by a value of 1. So we are going to use the HTTP client built-in class to make a HTTP GET request to the relevant Web API action method. So let's instantiate a HTTP client object like this. The HTTP class is a member of the system.net.http namespace. So let's ensure we include the relevant directive. Let's use a HTTP response message object to encapsulate the returned value, returned from our Web API component's relevant action method. So we need to run this line of code asynchronously, which means we need to include the await operator before calling the getAsync method. Note the getAsync method has the async suffix, so we know that this is an asynchronous method. Note the red squiggly line here. This is because in order to run this code asynchronously, we need to include the async modifier within our btn web API call _click event handler method's method signature. Note that we don't need to return a task object from this button click event handler method because this method is a high-level event handler. So we need to pass the URI of our web API action method to the getAsync method, so that the relevant action method is invoked on the server when the user clicks the button named btn web API call. So let's run our web API component by running the relevant web API project. So a GET request is made to the weather forecast controller by default. Remember, this code was auto-generated when we created our web API project. Let's change the URI within our browsers so that a GET request is made to the getAction method within our TestLongOperationController class. Let's refresh our browsers, and note a 5-second delay before the expected result is written to the browser window. So let's copy the URI that our browser is currently pointing to. Let's go to our UWP project and let's paste the URI here as a string argument to the http client.getAsync awaitable method. Let's call an awaitable method named readAsStringAsync to retrieve the content returned from our call to the web API component. Then let's write code to add the returned string to the list view component that we named LVW output. We can do this through a call to our private method named addListItem. So let's move the code that increments the _web API counter variable to just above where we have added our string result to the list view component. So we need to ensure that our web API project is first running before we run our UWP client code, so let's do that. Let's run the UWP project so we can test the performance of our user interface. Let's first test that we are able to get a result back from our web API component. So let's click the button labeled Web API Call. Great, the result appears on the list view as expected. The result is added to the list view, and we can see it as output on the client side, displayed within the list view component. Notice that there was a delay before the result appeared in the list view because we want this call to emulate awaiting a long-running operation. Now let's test that when we execute this long-running operation, that the UI thread is not blocked. The UI thread should not be blocked because we are making our GET request to the Web API component asynchronously. So let's once again click the button to make our Web API request. And now let's click the other button several times to run our fast local operation several times. Great, and you can see that the local task is running even while awaiting the result from our remote long-running server-side operation. The UI thread is not being blocked, and our asynchronous code is working as expected. You can see that when the asynchronous operation completes, the appropriate result is added to the list view component. And while we were waiting for the relatively long-running asynchronous operation to complete, we were able to run several local fast operations. So the fast local operations are running concurrently with the long-running asynchronous operation. So let's make several requests to our Web API component, and let's also run our fast local operation concurrently several times. Great, and you can see by the output appearing in our list view component that the user's experience is smooth. The user's experience is not adversely affected when the long-running Web API operation is executed. The user is able to perform other operations using our application without the user's experience being impeded by other incomplete long-running operations. This is why the task-based asynchronous pattern is so powerful. This, in my opinion, is one of the reasons why the C# language is so powerful, because a lot of the complexity in making a long-running operation run asynchronously is hidden from the developer. This complexity is abstracted. the C# language makes the inclusion of asynchronous behavior in our applications easy to implement. Please download the code for yourself and play around with the code so you can experience how the relevant asynchronous code results in a far smoother user experience than if the same code were implemented synchronously. The links to the relevant GitHub repositories have been included below in the description. I hope you have enjoyed this video on using the task-based asynchronous pattern in our code to include asynchronous behavior in our applications. In my opinion, this is one of the most important concepts in C# programming. In an age where smaller devices are used to perform relatively long-running operations, we need to ensure that our users' experience with our applications are not adversely affected by poor performance of our applications caused by synchronous code implementations of relatively long-running operations. We can drastically improve the performance of our applications by running these relatively long-running operations asynchronously. This is now easy to achieve using the C# programming language. Please consider subscribing for more content on advanced C# concepts and much more. And please ring the bell so that you'll be notified of future content released from this channel. If you feel you've gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released on this channel with anyone you feel may benefit from their content. I of course love reading your comments, so please feel free to share your thoughts with me in the comments section. As always, the code examples that were created in this video can be downloaded from GitHub. A link to the relevant GitHub repositories can be found below in the description. Thank you, and take care. Hi, and welcome to the second part of a tutorial on asynchronous programming using the C# programming language. This video is also the second part of the 6th tutorial in an advanced C# course. In the first part of this video series on asynchronous programming using C#, we specifically focused on the async modifier, the await operator, and the task object. We discussed that there are essentially two CPU blocking operations that we may encounter when developing our applications, namely I/O-bound operations and CPU-bound operations. These CPU blocking operations can result in poor performance of our applications and ultimately result in a poor user experience, UX, with our applications. With the increased use of smaller devices that may not have the capabilities of, say, for example, a notebook or desktop computer to handle resource-intensive operations, it is essential that we apply coding methodologies in our applications to ensure that the users are not negatively impacted by potentially resource-intensive CPU-bound or I/O-bound long-running operations. The way C# developers can solve these UX issues is through the implementation of asynchronous code. The C# programming language makes available several methodologies that can be implemented in our code to achieve asynchronous behavior, namely Asynchronous Programming Model, APM. This was covered in part 3.5 of this advanced C# course, Event-Based Asynchronous Pattern, EAP, and the Task-Based Asynchronous Pattern, TAP. Microsoft's recommended approach to implementing asynchronous behavior in our C# code is to use the task-based asynchronous pattern. I recommend that you watch the first part of this video series before watching this video. For more videos on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content released from this channel. So in the first part of this video series on asynchronous programming in C#, we focused on how to apply the task-based asynchronous pattern to handle the negative UX effects that can be caused by long-running I/O-bound operations. In this video, we'll focus on how to apply the task-based asynchronous pattern to handle the negative impact on the user's UX that can be caused by long-running CPU-bound operations. So let's start by briefly going over what is meant by I/O-bound operations and CPU-bound operations. I/O-bound tasks are delegated to the I/O subsystem. And while the relevant I/O-bound operation is handled the CPU thread on which the IO-bound operation was invoked is blocked from running any other operations. So while the relevant IO-bound operation is running, the CPU is idle. All other operations are blocked from being processed by the CPU. This can mean that if the relevant operation runs for a relatively long period of time, that a delay in the user's interface responsiveness can be noticed by the user. This means the user's experience is negatively impacted by the relevant, relatively long-running IO-bound operation. So the characteristic of non-CPU-bound processes is that they don't occupy the CPU when they are performing other operations like IO-bound operations. IO-bound operations include tasks such as writing to your hard disk drive, waiting for a response from the network, or querying a database. These operations cannot be sped up by fast local processing, as performance is constrained by the I/O subsystem's hardware and performance. The hardware drive's write speed will dictate how long something takes to be written. The third-party server response time will determine how quickly you can process a request. CPU-bound means the limiting factor in a particular task or algorithm is doing calculations. The only way to speed up the relevant CPU-bound operation is increased CPU power. Adding more memory, a faster I/O, for example, will not help. Examples of CPU-bound tasks are video-audio content conversion compression algorithms, search algorithms, graphics processing, rendering games or videos, heavy mathematical computations like calculating factorials, matrix multiplication, finding prime numbers, etc. Encryption, decryption operations. So basically tasks that require the CPU to perform computations. So tasks that perform particularly intensive calculations may cause performance issues and ultimately UX issues when a user runs our applications. The asynchronous handling of CPU-bound operations are implemented differently than the way I/O-bound operations are implemented. For a comprehensive explanation of how we can handle I/O-bound operations asynchronously in C# code, please view the first part of this video series. In this video, we'll focus on handling CPU-bound operations asynchronously. So let's look at a code example where we'll run a number of CPU-bound operations in parallel to one another. Which, as we'll demonstrate, will result in an overall performance advantage over running the same CPU-bound operations synchronously. So let's create a console application and name it Financial Trading Platform Application. So the theme of this code example is a trading platform. The user of this application can analyze stock market charts that will include technical indicators to help the user decide to open or close a position regarding a particular stock. I'm going to drastically simplify this code example so that we can focus on the principles involved in running multiple computational operations asynchronously. The technical indicator information that will be presented with the relevant stock chart will be calculated on the fly. So in this example, the technical indicators that will be calculated on the fly and presented to the user with the relevant stock chart are, for example, stochastics, fast-moving average, slow-moving average, and Bollinger Bands. I'm not going to go into detail regarding the meaning of these technical indicators. Basically, they aid the trader in deciding whether a stock is overbought or oversold, or whether it has growing price momentum or losing price momentum. Ultimately, these technical indicators aid the trader in the trader's decision to buy or sell a quantity of a particular stock. So, for example, the stochastics, the fast-moving average, the slow-moving average, and the Bollinger Bands can all be calculated in parallel to one another. These calculations can be coded to run concurrently rather than consecutively. So let's create a public class named Stock Market Technical Analysis Data. Let's create a constructor in our new class. Just for the sake of making this example feel more authentic, let's add 3 parameters to this constructor. We are going to keep this example very simple, and these parameters will not actually be utilized. The arguments passed into these parameters would be used as query criteria when getting the raw stock market data from a remote source. So the first parameter is stock symbol as string, representing a particular stock that the user wishes to analyze. For example, Apple, Amazon, Tesla, Anglo Gold, whatever it might be. The second parameter represents the start date and is defined as date time. The third parameter represents the end date and is also defined as date time. So the date time arguments passed into the second and third parameters will represent time period criteria pertaining to the time period over which the relevant stock market data was captured. In the interests of keeping this example simple, and in the interests of time, we are not going to include any code within this constructor. Let's simply comment that code would go here for retrieving data from a remote server. So let's use our imaginations and say that an IO-bound asynchronous HTTP request is made to a Web API component to download the relevant raw stock market data within this constructor. This data will be used to calculate relevant technical indicator information so that the user can glean meaningful information from the downloaded raw stock market related data. So let's create a few methods. The first 4 methods won't be all that computationally intensive. The first 4 methods will be responsible for getting the daily, opening, closing, high, and low prices for the relevant stock. We'll then include the more computationally intensive methods in this class, i.e. the methods used for calculating the relevant technical indicator information. For example, the stochastics, fast-moving average, slow-moving average, etc. So the first method will be responsible for performing an operation to get the daily opening prices for the relevant stock from the raw data that is retrieved within the constructor. So this method is appropriately named getOpeningPrices. So the returned values for all of these methods defined within this class will be an array of values of type decimal. This method will return an array of decimal values representing the opening prices for the relevant stock. So in each of the methods we'll create for this class, we'll write the method's name and the thread ID representing the thread on which the method will run to the console screen. We are going to run multiple methods in this class on multiple threads concurrently. So let's write code to output a narrative to the screen, which will serve as a substitute for presenting the actual data that would be required in a real-world application. To represent the duration of time the operation performed by the relevant method could take, let's make the thread on which the method will run sleep for a specified amount of time. So for this method, which won't require much computation, we'll make the thread of execution sleep for 1,000 milliseconds, which is 1 second. And then let's just return an empty decimal array. The data in this example is not important. In this example, we want to focus on the asynchronous principles rather than the real-world trading platform example that this code represents. Okay, and the other methods can be implemented in much the same way. Let's copy this method, and let's paste it 8 times. Then let's modify the code appropriately for each method. So the next method is named getClosingPrices and is responsible for retrieving the daily closing prices of the relevant stock from the raw downloaded stock market data. Let's say it runs for 1,000 milliseconds. The next method is named getPriceHighs. This method is responsible for getting the daily highs for the relevant stock. This operation also runs for 1,000 milliseconds. The next method is named getPriceLows. This method is responsible for getting the daily lows for the relevant stock. Let's say this method runs for 1,000 milliseconds. So all of the methods that we have added so far run for 1,000 milliseconds. Now we are getting to the methods that are more computationally intensive. This method is named calculateStochastics. This method is responsible for calculating technical indicator information to help a trader decide whether a stock is overbought or oversold, which ultimately aids the trader with the decision to buy or sell a quantity of a particular stock at the current stock price. So let's say that this may be a particularly computationally intensive operation. So let's say this operation takes 10 seconds to complete. So let's pass in an argument of 10,000 milliseconds to the thread.sleep method. The next method is named calculateFastMovingAverage. Let's say that this operation is also computationally intensive, so let's put the relevant thread to sleep for 6 seconds. The next method is named calculateSlowMovingAverage. Let's put the relevant thread to sleep for 7 seconds. The next method is named calculateUpperBound Bollinger Band. The next method is named calculateLowerBound Bollinger Band. Let's put the relevant thread to sleep for 5 seconds. Let's put the thread on which this method runs to sleep for 5 seconds. The Bollinger Bands can also be used by traders to ascertain whether the relevant stock is overbought or oversold, which ultimately aids the trader's decision to buy or sell a quantity of the relevant stock. So you can see that the last 5 methods in this class could potentially be computationally intensive, as these methods perform the operations of calculating technical indicator information from potentially large amounts of raw stock market data. So let's go to the main method, where we'll write code to call the methods that we have just created in our stock market technical analysis data class. So let's first write to the console screen that the main method is being called. In this output to the screen, let's include the ID of the thread on which the main method will run. We can get the thread ID from the thread.currentThread.managedThreadID property. And we also want to include the thread name, which of course is the main method. So let's first demonstrate running the first 4 methods in the stock market technical analysis data class synchronously, so that we can later run these methods asynchronously and then compare the performance difference. So let's instantiate a new object from our stock market technical analysis data user-defined type. Let's say we want to download raw stock market data relating to the fictional stock represented by the symbol of STKZA for data captured between the dates 1st of January 2010 and 1st of January 2020. So we want the specified stock market data for a particular stock captured over a specified 10-year period. Let's write code to run these methods synchronously. So let's call the getOpeningPrices method. Then the getClosingPrices method. Then the getPriceHighs method. And lastly, the getPriceLows method. So in order to see how long it takes for all 4 methods to complete, let's capture and store the current date-time value captured before we call the relevant 4 methods. Then let's subtract the date-time value captured before the 4 methods are run from the date-time value captured after our 4 methods have completed. We are doing this so that we can see how many seconds have elapsed between the time we started to run our 4 methods and the time the operations carried out within these methods completed. So each of these methods have been coded to take 1,000 milliseconds or 1 second to complete. Let's add a method that denotes adding the relevant data to the stock chart that will be displayed to the trader. Let's name this method Display Data on Chart. To keep things simple, we can simply write a message to the screen representing that this method has displayed the chart with all the requested data, including relevant technical indicator information, to the trader. So let's run the code. And we can see from the results that all of these methods are running synchronously on the main thread. The thread ID of all of these methods is 1. We can see that each method ran consecutively. We can see this because each of the 4 methods ran for 1 second and a total of 4 seconds was taken for all 4 methods to complete. So now let's run these methods asynchronously using the task.run method. So let's create a generic list to store the generic tasks that accept an array of decimals as the generic argument. Remember, each of our methods within the stock market technical analysis data class return an array of decimal values. Let's ensure that we include the relevant directives. So we need to include the system.threading.tasks directive, and we also need to include the system.collections.generic directive. To be explicit, let's first create our generic task objects and appropriately encapsulate the 4 method calls. And note that the generic argument for each of the generic task objects is an array of decimal values because each of the relevant methods that the task objects encapsulate returns an array of decimal values. Right, let's write the code to add each of the methods encapsulated within the task objects to our list. Now we can use the task.waitAll method to block the main thread until all the tasks have completed. So all of our tasks will run in parallel on background threads, and the main thread will be blocked by the task.waitAll method until all 4 methods have completed. For more information on the task.waitAll method, please navigate to this URL. So we need to pass our list of tasks to the task.waitAll method. But the task.waitAll method expects an array, so let's use the toArray method to explicitly cast our list of generic task objects to an array of generic task objects. So at this point in the code, i.e. after the task.waitAll method call, we know that all of our tasks have completed, so we can get the results of each of our tasks like this. Great, let's run the code. If we look at the output, we can see that the threads on which each of these methods ran have different thread IDs. Behind the scenes, our code has run these methods on different threads. When we ran these methods synchronously, these methods ran consecutively and ran on one thread, the main thread. So I've noticed there's a little problem with the text output. It says 1 seconds and should say 1 second. So let's add a ternary operator to our code so that when 1 second has elapsed, our code outputs 1 second rather than 1 seconds. We only want to output seconds if the time that has elapsed is greater than 1 second. Let's run the code to check our fix. Great! So let's write code to run all 9 methods synchronously, and after this, we'll run all 9 of these same methods asynchronously. So we'll now be running some of the more computationally intensive methods within our stock market technical analysis data class in this demonstration. Let's run the code. And you can see that there is a significant time lag when running this code synchronously before all our methods complete and output is presented to the screen. Let's write the code to run our methods asynchronously using the task.run method. Right, let's run the code. You can see by the thread IDs outputted to the screen that our methods are not running on the main thread and are running concurrently on background threads. So in this video, we have covered the basics of running multiple CPU-bound operations asynchronously. In this video series on asynchronous programming in C#, we have covered the basics of how we can improve performance of our applications through asynchronous programming when encountering either of the two types of blocking operations, namely I/O-bound operations and CPU-bound operations. In the next video, we'll look at the best practices and caveats of which we must be cognizant when running I/O-bound and CPU-bound operations asynchronously. For more content like this and much more, please consider subscribing and please ring the bell so that you'll be notified of future content released from this channel. If you feel you've gained value from viewing this video, please smash the like button. It will be greatly appreciated. Please feel free to share any of the videos created by this channel with anyone you feel may benefit from their content. I love reading your comments, so please feel free to share your thoughts with me in the comments section. All code created in these videos can be downloaded from GitHub. Please see below in the description links to the appropriate GitHub repositories. Hi and welcome to the third part of a tutorial on asynchronous programming using the C# programming language. This video is also the third part of the 6th tutorial in an advanced C# course. In the first and second parts of this video series, we looked at how to apply asynchronous code so as to alleviate the negative effects of blocking operations on an application's UX, user experience. Certain long-running operations performed by our applications can be the source of poor performance of our applications. For example, long-running operations performed from WPF, UWP, or Xamarin applications can cause the UI, user interface, to be periodically unresponsive. This can be frustrating for the user of our applications. The user will have a suboptimal user experience. C# provides us as developers with appropriate tools to handle these long-running operations asynchronously with relative ease. So let's discuss the difference between I/O-bound operations and CPU-bound operations, and this will set us up for later when we create a code example to help us understand best practices when applying asynchronous code to handle I/O-bound or CPU-bound operations. So in this video series, we have already discussed that the two kinds of CPU blocking operations are CPU-bound operations and I/O-bound operations. CPU-bound operations are operations that perform computations that need to be handled by the CPU, for example, mathematical operations, encryption-decryption operations, graphics-related operations, financial calculations, etc. Basically, computational operations. I/O-bound operations are operations that are delegated to the I/O subsystem to perform tasks such as writing to a hard disk drive, engaging the I/O subsystem to perform requests across the network, file handling operations, etc. We discussed that I/O-bound operations are more commonly encountered than CPU-bound operations. I/O-bound operations are also generally a lot slower than CPU-bound operations. So this video is about best practices when applying asynchronous code in our applications. Please view the first and second parts of this video series on asynchronous programming for a foundational understanding of I/O-bound operations and CPU-bound operations in the context of asynchronous programming in C#. The recommended coding methodology provided by Microsoft in the C# language to create asynchronous behavior in our applications is known as the Task-Based Asynchronous Pattern, TAP. Over the last two videos in this series, we have discussed why we should implement asynchronous code. The simple answer is to improve the performance of our applications. In this video, let's clarify the best practices when applying writing code to run the relevant code asynchronously. Let's start with I/O-bound operations. As we have discussed, I/O-bound operations refer to operations like, for example, file handling operations, making requests across a network, writing data to a database, reading data from a database, etc. Operations that engage the I/O subsystem. We can handle I/O-bound operations asynchronously, both on the client side, for example, in WPF, UWP, WinForms, or Xamarin applications. We can also handle I/O-bound operations asynchronously on the server side, in, for example, Web API or ASP.NET MVC applications. I/O-bound operations can be handled using async await. In simple terms, an asynchronous method that returns a task object can be preceded with the await operator, which means we can run the operation asynchronously using async await. So, for example, for a .NET client application, a button is clicked. Within the button click event handler method, an asynchronous method is invoked. So the asynchronous method is invoked on the UI thread. This means that immediately after the asynchronous method is invoked, the UI thread is free to be utilized to process other operations. The user interface, UI, does not freeze while the asynchronous method is running. The user is able to, for example, click other buttons and invoke other operations that can be invoked on the UI thread. When an asynchronous method is called to perform the relevant I/O-bound operation, the task is immediately delegated to the I/O subsystem. And instead of blocking the CPU, as would be the case if we were running the I/O-bound operation synchronously, the async modifier and await operator instruct the .NET runtime to ensure that the CPU is not blocked during the running of the I/O-bound operation. This means that other operations can utilize the CPU even while the I/O-bound operation is running. Very briefly, what is happening is that when the .NET runtime encounters the await operator, as discussed, the thread on which the operation is invoked, on the client this would be the UI thread for example, is immediately released. So at this time, code in the relevant method is suspended, i.e. the lines of code that follow the line of code that contains the await operator in the relevant method will not be executed until the asynchronous I/O-bound operation completes. While the asynchronous I/O-bound operation is running, however, the UI thread can be used to process other operations, for example, invoked from clicking another button on the UI. But a promise is returned to the line of code containing the await operator is made. So when the relevant asynchronous operation completes, the .NET runtime returns to the line of code containing the await operator, returns a value if required, and continues to execute the lines of code from that point in the relevant method. So the key point of this explanation is that unlike for CPU-bound operations, I/O-bound operations generally don't require additional background threads. In this example, the .NET runtime is delegating the I/O-bound operation to the I/O subsystem and not to a new thread required from the thread pool. So I think before we continue, let's ensure that we have a clear understanding of what is meant by the following terms: thread and thread pool. Let's start with the term thread. A thread in computer science is short for a thread of execution. Threads are a way for a program to divide itself into two or more simultaneously or pseudo-simultaneously running tasks. Thread pool. A thread pool is a group of pre-instantiated idle threads which stand ready to be given work. So, a thread pool is created so that threads are readily available to a program, which means when a program requires a thread, the program can acquire the thread from the thread pool rather than incur the overhead of instantiating a new thread. So, let's go back to the example demonstrated in the second part of this video series, where the task.run method was used to run CPU-bound operations. We demonstrated how each method that was run through the implementation of the task.run method was run on its own dedicated background thread. So each time the task.run method is invoked, a new thread is taken from the thread pool and used to run the relevant CPU-bound operation. So this resulted in the methods that encapsulate the CPU-bound operations running concurrently, i.e. asynchronously, rather than running one after the other, i.e. synchronously. If you haven't yet viewed the second part of this video series, please view this video for a foundational understanding of running multiple CPU-bound operations concurrently on multiple background threads. So the key takeaway here is that when an I/O-bound operation is run using the async modifier and the await operator, a background thread is not required to handle the operation. The operation is delegated by the .NET runtime to the I/O subsystem. When a CPU-bound operation is run using the task.run method, a background thread is used to run the operation in the background concurrently with the main thread of execution. So now, with a foundational understanding of the differences of how I/O-bound and CPU-bound operations are handled asynchronously, let's look at best practices regarding implementing each of these types of operations asynchronously. So with running I/O-bound operations asynchronously, there's less to be concerned about, simply because of the way the I/O-bound operations are handled under the hood. I/O-bound operations can be delegated to the I/O subsystem, and the need to use additional background threads is not necessary. With running CPU-bound operations asynchronously, under the hood, the .NET runtime employs additional background threads to run the CPU-bound operations. This, for example, means that multiple tasks can run on the additional background threads concurrently. There may be times where using multiple threads is undesirable and may not result in the desired performance benefit. There are times when running multiple threads to perform tasks in parallel may result in an overall poorer performance. An example of this is running CPU-bound operations from within server-side code, for example, code implemented for ASP.NET MVC applications or code implemented for Web API components. We'll discuss why CPU-bound operations should be run synchronously under these scenarios a bit later in this video. So let's create a code example to help us understand best practices when confronted with issues relating to asynchronous programming in C#. The theme of this client application will be the same as the theme we used in the previous video in this series, i.e., a financial trading platform. So in the last video, we created a console application to get a general idea of running CPU-bound operations. In this video, let's create a new blank UWP project. UWP stands for Universal Windows Platform. Let's name this project Financial Trading Platform UWP. Let's set up a basic UI, user interface. Let's drag a button onto the designer surface Let's enlarge this button a bit. And name it BTN Fast Local Operation. Let's label this button Fast Local Operation. Let's drag another button onto the designer surface, just below the button we have just added. Let's name this button BTN CPU Bound Operations. Let's label this button CPU Bound Operations. And lastly, let's drag a list view control onto the designer surface and position this control to the right of our buttons, like this. Let's name this list view control LVW output. So before we add code directly to this file, let's add another project to this solution. We want our code to be reusable across both server-side and client-side projects. So let's create a standard library project to our solution and let's name this project Stock Market Component. Let's add a reference to the Stock Market Component standard library project from our UWP client project. Let's delete the class file that has been generated in our standard library project and let's add a class named Stock Market Data to our project. Let's add a method named getDataAsync. This method represents retrieving relevant stock market data from a server, so it is an I/O-bound operation. The method will return a string to the calling client code. So let's include the async modifier in the method definition, as well as a generic task type that accepts a string as the data type argument. Notice that we have included the async suffix in our method name. This lets the developer know that this is code that should be called asynchronously. So when the calling client code writes code to call this method, the developer should include the await operator preceding the method call, as well as include the async modifier in the method definition of the method where the relevant async call resides. So in the interests of time, we'll simply include placeholder code for this method. So let's use the task.delay method to represent the time that the work could take to carry out our relevant I/O-bound task. So let's say this process takes 5 seconds. So let's pass 5,000 milliseconds to the task.delay method. Let's then simply return a string value representing the stock market data that has been retrieved from the remote server. So let's simply return the literal text stock market data from this method. We must also include the await operator preceding our call to the task.delay method. Let's add a new class, and let's name this class Stock Market Data Analysis. So let's add a constructor that contains a parameter named data, which will represent the downloaded stock market data. For the purposes of this example, we don't need to include any code within the constructor. So very much like the code example in the previous video of this video series, let's include methods that calculate the technical indicators that the user of our application can use to aid the user's decision to buy or sell a quantity of a particular stock. The technical indicators that we'll refer to in this example will be the fast-moving average, the slow-moving average, stochastics, and Bollinger Bands. If you're not familiar with these terms, don't worry. The only thing that you need to know to follow along with this example is that calculating the data for these financial trading-related technical indicators are CPU intensive. They are CPU-bound operations. This is why I've chosen these technical indicators for this example, i.e. to serve as intensive, long-running, CPU-bound operations. So let's include a method to calculate the fast-moving average. So for these methods that represent CPU-bound operations, we can simply put the current thread to sleep for a specified amount of time, representing the time that the relevant operation may take to complete. So for this method, let's put the thread to sleep for 6 seconds. Then, for the purposes of this demonstration, let's simply return the method name and the thread ID to the calling code. Let's duplicate this method 3 times. These additional 3 methods represent the calculation of other technical indicators. So we can maintain the general structure of the methods that we have just created as they are, and simply change the method names and the time durations that represent the time the method takes to complete. Please note that the time durations that are being specified here are completely arbitrary and have been chosen only for demonstration purposes. So this method represents calculating the slow-moving average. Let's name this method calculate slow-moving average. Let's put the relevant thread to sleep for 7 seconds. This method represents calculating the stochastics. Let's name this method calculate stochastics. Let's put the relevant thread to sleep for 10 seconds. This method represents calculating the Bollinger Bands. Let's name this method calculate Bollinger Bands. Let's put the relevant thread to sleep for 5 seconds. Great, so let's say that we now have a reusable standard library component for calculating stock market technical indicator information completed. So just to confirm that we have already referenced this reusable component from our UWP client application. Great, so let's add some code to add the output of our methods to our list view control that we named LVW output. So let's create a private method named addListItem. So you're of course welcome to follow me as I create the code for this method, or you can of course copy the code from GitHub. A link to the relevant GitHub repository is available below in the description. Great, so let's include code within our button-click event handlers. To create a button-click event handler definition, we can simply go to our designer surface and double-click on the relevant button, like this. So we are first going to create code for the fast local operation. So let's create the button-click event handling method definition for the method that will execute our CPU-bound operations. These CPU-bound operations are encapsulated within the methods in our stock market data analysis class that reside in our standard library project. Let's ensure that we have a directive to the stock market component namespace. So let's instantiate an object from our stock market data analysis class, which resides in our stock market component standard library project. For now, let's simply pass in the literal text data to the constructor of the stock market data analysis class to represent the raw stock market data downloaded from a remote server. So let's write code first to run all of these CPU-bound operations in parallel to one another in much the same way as we demonstrated in the code example in the previous part of this video series. So firstly, let's create a list of generic task objects that accept the string data type as their data type arguments. So we know that the task.run method returns a task object or generic task object. The methods we wish to call all return strings, so each item in the relevant list must be strongly typed with a generic task object that accepts the string data type as an argument. Right, so let's add the tasks we wish to run to our list, like this. Then we can call the task.waitAll method, and in a bit I'll explain why the task.waitAll method is not the best method to call in this context. So in the code following the task.waitAll method, we know that the relevant methods that have run asynchronously have completed, so we can add the returned values from our methods to our LVW output list view control. Let's write the code to do this. Right, let's run the code. So now when I press the button marked CPU bound operations, notice that our UI is unresponsive when we try to perform any other operations. So I'm attempting to click the button marked fast local operation. The button cannot be clicked because the screen is frozen, and therefore the output from this action is not presented to the screen in our list view component. The UI is unresponsive when I click the button labeled fast local operation, because the UI thread is blocked. We have written our code to run a batch of methods asynchronously, but we have also written code to block the UI thread while our CPU-bound operations are running. The waitAll method blocks the UI thread until all the relevant tasks have completed. So even though the CPU-bound operations, like for example, calculate stochastics, calculate fast-moving average, etc., are running in parallel to one another on background threads, which will give us a performance advantage, the UI thread is being blocked while these CPU-bound operations are running. This is not ideal. So we can solve this issue because we can in fact use the await operator when running a batch of CPU-bound operations. We can achieve this by using the whenAll method instead of using the UI blocking waitAll method for running a batch of CPU-bound operations on background threads. So let's replace the waitAll method with the whenAll method. For more information on the whenAll method, please navigate to this URL. So please note that the waitAll method does not return a task object or generic task object. So this means we cannot call this method using async await. The waitAll method blocks the UI thread until the tasks within the relevant batch have completed. The tasks will be run concurrently on separate background threads, but the UI thread will be blocked while the tasks are running. The whenAll method, however, does return a task object or generic task object. This means we can call the whenAll method using async await, which means that we can call the whenAll method to run our tasks concurrently without blocking the UI thread. The UI will still be responsive even while we are running a batch of CPU-bound operations when we are using the whenAll method. So let's proceed our call to the whenAll method with the await operator, like this. We of course need to also include the async modifier in the relevant button click event handler method's signature, like this. Let's run the code. Let's click the button marked CPU-bound operations. And now when we run the code, the UI thread is not blocked and we are able to perform the fast local operation while the CPU-bound operations are running in the background. We can perform other operations concurrently while the relevant CPU-bound operations are running. So the task.run method returns a task object or generic task object. This means we can use the await operator when we call a CPU-bound operation in this way. So to prove this, rather than calling a batch of CPU-bound operations as we are doing here, let's run just one of the CPU-bound operations using the task.run method. So let's run the calculate stochastics method using the task.run method. So we can call this method on a background thread asynchronously like this. Let's run the code. Let's click the CPU-bound operations button, and you can see that while the calculate stochastics method is running, we are able to click the fast local operation button. The fast local operation button can run concurrently with the operation performed by the calculate stochastics method. And as we have already proven, we can also run a batch of CPU-bound operations on background threads without blocking the UI thread using the when_all method. So let's change the code back to the way it was so that we can call a batch of CPU-bound operations using task.run, async await, and when_all. Then we could reuse this functionality because we have written our CPU-bound operations in a reusable library component. This brings us to an important best practice when implementing asynchronous code for CPU-bound operations. The developer should never include the task.run method within reusable components. Always let the developer decide whether to run an operation synchronously or asynchronously. So the consumer of the component should always have the choice to run an operation contained within, for example, a library component synchronously or asynchronously. In our example, we have chosen to run our operations encapsulated within the stock market data analysis component project asynchronously, but we could have chosen to run them synchronously. We have proven in our demonstration that running the CPU-bound operations asynchronously gives us a huge performance advantage. We did, however, have the choice to run these operations synchronously or asynchronously because the operations are not implemented to run asynchronously within any of the methods of the component itself, i.e., we have not implemented the task.run method within the stock market data analysis component project. So in the stock market data class, we have written an IO-bound operation that is responsible for downloading the raw stock market data from a remote server. This is different to a CPU-bound operation because it engages the IO subsystem and not the thread pool to acquire a background thread. So let's write code to run this IO-bound operation in order to download the relevant raw stock market data before calculations are performed from the raw stock market data. So we could invoke the IO-bound method lazily like this. So let's create a member variable named _data. Then within the relevant button-click event handler, we can check to see if the _data variable is null. If it is null, we can then run the IO-bound operation. If the _data variable is not null, then it means we have the data and can pass it into the stock market data analysis classes constructor when instantiating the relevant object. It is best to include the task.run method close to the relevant event handler method, as we have done here. We have control over whether we want to run these operations using the task.run method on background threads or run them synchronously. So calling the task.run method directly from the relevant event handler method, like for example a button-click event handler, is a best practice. Another best practice is that if the relevant method's code doesn't need to run on the original thread once the CPU-bound operations have completed, then we can in fact gain a bit of a performance boost by not returning to the main thread. The rule of thumb here is don't run code on the main UI thread unless you have to. So we can achieve this performance boost by using the configure await method. So the when_all method returns a task object, which implements the configure await method. This means we can call the configure await method like this. Notice we are passing in false